Space optimized dynamic programming for subset sum. Whatever you see here written, all these are what we learned in the last lecture about subset sum problem. We learned that we can solve this problem using dynamic programming. And what did we do in dynamic programming approach? We used a dynamic programming table of size n plus 1 cross s plus 1. Using this, we had solved the problem. What problem did we solve? Subset sum problem, in which from a given set of n numbers, we had to see whether it is possible to make a subset of those numbers such that the subset will sum to one particular value s. This is what we tried. In order to solve this problem, we had a dynamic programming table, and when we fill the complete table with the values of true or false on whether a subset of that particular size can give you a sum of that particular, whatever is the sum corresponding to that particular block. This is what we did. Finally, whatever is the value in the last block, that told us that using all the n elements to consideration, is it possible to make a total sum of s or not? This is what we found from the last block. We saw that the time complexity was order of n into s, and the same was the space complexity. Here, we are going to see whether it is possible to decrease the space complexity down from order of n into s to order of s. Is this possible is what we want to see. In order to do this, what did we say in the last lecture? There is one important observation that you want to make. The observation is, while we went through this complete algorithm, at any point, whenever we wanted to fill dpij, that is any particular block in the matrix, the only consideration was the previous row. That is, if you see this, it is dpi minus 1j. I minus 1 corresponds to previous row. Similarly, here, two elements we considered were, one was I minus 1j, again previous row, or I minus 1, j minus a of I minus 1. This is also previous row, which means while filling this table at any particular point to fill any particular block in a row, the only consideration was the row right above it. All other rows were irrelevant. What can we learn from this? Instead of the table, if we just maintain an array which will keep track of all the elements in the previous row, this should be good enough for us to fill the complete table. This is what is the taking from this. Let us try to apply this logic and see how can we decrease the space complexity. See, as I said, there is a reason why in the dynamic programming lectures, I always teach you the table approach first, and then we'll go to the array approach or whatever space optimized approach is possible. The reason is the table approach is logical. It tells you exactly what is happening, exactly what is each entry in the table, and that makes a lot of sense. Once you understand the algorithm, you are clear of what is happening. Then if you convert this table into an array, it is easy for you. That is the reason. Let us make the required changes in this algorithm. We'll make here only so as to work it with an array instead of table. So the first change is, instead of this n plus 1 cross s plus 1 table, you'll simply have an array. And what would be the size of the array? It should be s plus 1 sized array. Okay. So now, instead of table, you only have an array. Next question is, what is each element of this array representing? Previously, each element of the table dpij told you whether it is possible with the first I elements to make a subset sum of j. This time, any particular element dp of j, let us say dp of j is your element, this will tell you whether at this particular point a subset sum of j is possible or not. What is this particular point? Whether it is a point at which you have considered first two elements, first three elements, first four elements, whatever, that you have to keep track separately. That is, in the loop you will keep track which are the elements that you have already considered. The array will simply tell you whether for this particular stage, whichever you are considering right now, whether a subset sum of j is possible or not. This is only thing that the array will tell you. Okay. So what should be the next step? The initialization. Previous initializations, what were those? First row was all true and the first column was all true and the first row was all false. This time you don't have column and rows. Instead of this, what can you say? Instead of all these, you have only one array. You don't have all these columns and rows concept. But for this array, first element, that is dp of 0, this will always be true. Why will this be true? This is corresponding to sum is equal to 0. So whether you have any elements, you have 1 element, 2 element, 10 element, 100 elements, whatever, sum of 0 is always possible. That is because take an empty subset, that is no elements there, then it will give you a sum of 0. So your first entry in the array dp of 0, this will always be true. What is the other thing? Next thing is, how are you going to make these updates? Here the updates were for dpij. The conditions will remain the same, that is if ai minus 1 is greater than j, then dpij was copied from the previous row. Whatever was the same column in the previous row, that is dpi minus 1j, that was copied to the present element. Instead of this, what can you do in the present scenario? Present scenario, instead of copying the previous row, you can say, I'm not making any changes. My row will stay as it is. So whatever be this particular block, this particular element, it will stay as it is in this iteration, which means you are preserving the value of previous iteration. What does previous iteration correspond to? Previous iteration will correspond to the previous row. That is the logic. So in this case, you won't make any changes. That is the reality. I'll simply write here dp of j is equal to dp of j so that you understand there are no changes. But the reality is, in algorithm, you won't write this step at all. You don't want to make any changes. Next thing, if ai minus 1 is lesser than j, that is this particular element under consideration, if that is lesser than or equal to j, then we said you have two possibilities. One is consider this element or not consider this element. What did we do in the previous lecture for dp? We considered dp I minus 1j, which is now dpj only. So this time instead of ij, you will be updating dp of j. For this, I minus 1j means you will simply keep the same value dp of j from the previous iteration. Or the other one is I minus j minus a minus 1. Here also what will you do? From the previous iteration, you will simply preserve the value of j minus a minus 1. But there is a catch. The catch is, if your array is something like this, this is your dp array, just think this is your dp array, and you're filling the elements from left to right, what will happen is, you would first fill this element for this new iteration, then the next element for the new iteration, next element for the new iteration, and so on. Let us say you are at a point where you are filling this element. What will you consider? One is the same element from the previous iteration. So as of now, you have not altered this entry. So whatever entry is there is from the previous iteration. It is good. Next thing is j minus ai minus 1, which is some block which is before this. Whatever be that block, you have already altered that block in the new iteration, which means you can't get this old value now. This is the value that you need from the previous iteration. In order to avoid this error, what should you do? You should never fill this array from left to right. Instead, while you are looping, always fill this from right to left. Then what is the advantage that you get? At any point, that particular element under consideration and all the elements before that will all be the entries of previous iteration. So you can refer to all these and fill this element. Because of which, always iterate from right to left and not from left to right while you are using this array implementation. See, it is because of these complexities that I didn't explain array implementation initially. We went for the table approach. Now that you know the logic, it's easier for me to tell you that, see, instead of left to right, you should go right to left, because this is the problem. It's easier for me. So what is the next step here? Instead of these steps, how should you write these things? I am erasing these things off. We'll rewrite this now. How are we going to rewrite these things according to the array approach? If we rewrite, let us write this as a function. That should make more sense, I think. So we'll have a space optimized subset sum. Let us say subset sum which is optimized. Okay. You have an input array A and you have, what do you have, a sum S. These are the things that you have. You want to make a total sum of S. You want to see whether it is possible or not. First thing is the DP array. What should be the size of DP array? It should be of size S plus 1. Let us say you have all false to start with. Your array is having all false values. What should you do then? It is initially all false. You want to see whichever entries will become true as you go through the iteration. First thing is dp of 0, first element, this should be made true. Why are you making this true? Because this corresponds to sum is equal to 0. When sum is 0, always that particular subset sum is possible, because just don't consider any elements, sum will be 0. Next step, you have to start the loop. In loop, what did we learn just now? For you should loop for each element, that is I equal to 0 to n minus 1. For each of the elements, you need to do this loop. Inside the loop, what should you do? We learned that inner loop should not be from left to right. Inner loop is what is actually filling the array. This loop is simply considering each element to be considered. Each iteration is for each element. In the inner loop, you should always do from right to left, because we already learned right now that filling of this array should be done from right to left. What should you do now? For the value j, j's value will be from s to 1. Why is s to 1? Because s equal to 0 case is anyway true. You don't have to do anything. It's always true. J equal to s to 1. This is to be done only when this array value is less than element. That is, if array, you have an array of I minus 1, this particular, that is ith element, whenever this is less than or equal to j, then only you have to execute whatever we are going to do. How can you write that? If the value of a of I minus 1, that is value under consideration, if this particular element is lesser than or equal to j, then what do you want to do? In case it is lesser than or equal to j, your value dp of j, this will be updated as dp of j, or this is an or statement, which means if either of the sides is true, you have to mark this as true. dp of j or dp of, what should this be? J minus a of I minus 1. This is what we want. So this is the logic is exactly same as what we learned in the last lecture, just that we converted matrix into array. Here, keep in mind that the alteration is to be done only when the value is lesser than sum. Otherwise, whatever is the value of dp of j, it will stay as it is. So we are not doing any alteration. In case the value is lesser than j, then you have two conditions. One is, in case dp of j is true, you can keep it as it is. If it is false, you have to see this element also, dp of j minus a of I minus 1. That is why I kept an or statement here. If either of these conditions is true, then this will become true. What should you finally return? Finally, you should return the value of dp of s. After all the iterations, you should return dp of s. What is the time complexity here? What is the time complexity of this algorithm? Time complexity is, here you can see we are looping through all the n elements. This is order of n. And then here you are going through, that is for each of the elements that are selected here, you are going through each entry corresponding to sum. So it is order of s here. Total time complexity is order of n into order of s, which is order of n into s. So the time complexity will remain same as the previous algorithm. But what about the space complexity? Space complexity will come down to order of S, because instead of the table which was sized n plus 1 cross S plus 1, here you have just an array which is sized S plus 1, because of which time complexity is order of S. This is the space optimized approach for subset sum.